Good day and Dangal greetings. This video presents the detailed system architecture of the Smart Campus Emergency Response Management System, or SCERMS. The system is built using custom data structures and modular Java packages that simulate how a real campus emergency response team would operate. Each subsystem was assigned to a specific team member, resulting in a fully integrated and cohesive emergency response solution. Greetings. I'm Ais for location functions using weighted graph. The campus navigation system relies on a weighted graph, which is essential for identifying paths, measuring distance, and determining travel times. Graph components and structure includes the graph is composed of vertices representing buildings, facilities, and important campus landmarks. Edges representing walkable paths with an associated weight. The weight can represent distance, terrain difficulty, travel cost, and time estimation. The system supports both directed and undirected graphs, allowing flexibility depending on campus layout or simulation requirements. Location management workflow. Location prompter gathers users' input for creating or updating location. Location manager stores all locations and handles location retrieval. Location controller integrates location data into the simulation. These components allows the system to do real-time pathfinding and adapt to changes in the campus layout. Routing the shortest path logic. The graph implementation supports searching for all adjacent locations, calculating shortest paths, updating path weights and connections. This forms the navigation layer that guides responders to most efficient route.
Greetings, my name is Clemeno and I will be the one explaining the unit management using a tree-level nested map. So in our Smart Campus Emergency Response Management System, managing responders efficiently is essential. So to achieve this, our system uses a tree-level nested map structure. So this allows the platform to organize, locate, and update all responder units with high accuracy and speed. The responders in the system are grouped based on three major attributes. So first is the location, which identifies where each unit is currently stationed. Second is the responder type, such as ambulance teams, rescue units, fire response groups, or security personnel. And third is the responder status, which indicates whether a unit is available, busy, or offline. So to handle these layers of information efficiently, the system uses a mapping structure that looks like this. So this three-level nested map allows the system to perform fast and organized lookups. Instead of placing everything inside a single huge hash map, this design prevents unnecessary rehashing and keeps the entire data structure more manageable. It also gives the system precise control when updating a particular responder status without affecting others. So the biggest advantage is the scalability. Responders types, statuses, or locations can be added without rewriting core components. So overall, this design ensures that during an emergency, our Smart Campus Emergency Response Management System can immediately identify the right responders, check who is available, and determine who is the closest to the incident, allowing for faster and more reliable emergency response. So that will be all. Let's proceed to the next presenter. Thank you.
Hi, my name is Maturan, and I'm here to explain the emergency case management using a binary search tree. So, without further ado, let's discuss this. So, in an emergency response environment, cases must be handled based on how urgent they are. They are not simply in the order they arrive. To achieve this, we use a binary search tree as the backbone of the emergency case management subsystem. So, a binary search tree is ideal because it does not just store information, it organizes it according to specific rules. Each incoming emergency case is compared using two important criteria: its urgency level, which may be classified as critical, high, medium, or low, and its timestamp, which ensures that if two cases shares the same urgency, the one that arrived earlier is treated as more urgent. When a new case enters the system, the binary search tree automatically places it in its correct position based on these comparisons. So, preserving a structure where the most critical and the earliest cases naturally rise to the top layers of the tree. This gives the system several powerful capabilities. It can insert new emergencies in real time without disrupting the priority order. Search and locate a specific case quickly using its keys or ID. And retrieve the most urgent case efficiently without scanning an entire list. Additionally, by performing an indoor traversal of the binary search tree, the system can generate a clean, comprehensively sorted report of all cases, from the least urgent to the most urgent, or vice versa, depending on the operation needed. Overall, this binary search tree driven method ensures that highly urgent cases are never delayed. The system remains efficient as the data grows, and emergency managers always have a clear and organized view of all active cases. This structured approach ultimately leads to faster response times, improved accuracy, and a more reliable emergency management workflow. So that's all for my part, and I thank you po.
Hello everyone, my name is Balois, and today I'm going to start with our part or my part in our program, which is the find the responder. Now this function is does the finds the closest responder to an emergency by checking which one requires the fewest steps on the map. It examines all possible paths and chooses the responder with the smallest travel count. Basically, it answers sino ang pinakamalapit na responder. Now, this function uses what we call a Dijkstra algorithm. Now, what is a Dijkstra algorithm? This one is a most efficient algorithm to traverse in a graph to find something, or like for example in our program, para malaman natin kung sino ang pinakamalapit na responder to an emergency by checking which one requires the fewest step. This one requires Dijkstra. Now for the second function we have most urgent case getter. Now this one is dedicated for BST, binary search tree. This function gets the most urgent emergency by going to the very rightmost node of the BST. In our setup, the rightmost node always represents the highest priority. It simply answers ano ang pinaka-urgent na emergency ngayon. Now, BST, with the BST nature, every highest node or every highest data of a BST goes in the right node or the right side of the BST, and the lowest one does go to the left side. Now BST, with that being said, highest priority will go always to the right and lowest priority will always go to the left. Kaya tayo nagsa-search to the right. Now this third function we have is shortest path. This part counts how many steps or hops are needed to move from one location to another on the map. It doesn't calculate the real distance, just the number of the nodes you pass through, and uses by consumer to update the both current node and step count at the same time. That's the system ano karaming talon ang para makarating. Gumagamit to ng by consumer dahil needed talaga mag mag like mag-store ng dalawang data while we traverse. And lastly, our simulate controller. This one is the most important one. This acts as like the general controller of everything, and this part automatically assigns responders to emergencies. It always handles the highest priority emergency first, finds the nearest available responder, assigns them, and repeats until all emergencies are processed. Basically, it works as the system's auto dispatch manager. Thank you so much.
Outro. The SCERMS architecture demonstrates how custom data structures and modular design can be combined to simulate real-world emergency management. Each subsystem, routing, prioritization, unit management, and dispatch, was built with both efficiency and clarity in mind. Together, these components form a robust and intelligent system capable of supporting critical emergency operations across a campus environment.